Hello guys, in this video I'm going to show you where this equation comes from. This equation describes the voltage across this capacitor after time t0. If we apply KCL on this node right here, the equation that we get looks like this. Now, before we solve this equation, since this is a first-order differential equation, let's look at a more general form of first-order differential equation. So this is how a first-order differential equation looks like. To solve this equation, we need to make an integral factor that comes in this form. The important thing to note about this integral factor is that if we find the derivative of this function with respect to dx, we get the same mu times p of x. So if we multiply mu on both sides of this equation, the equation that we get looks like this. And since mu times p of x equals the derivative of mu, we can rewrite this equation in this form. And this left part would in fact correspond to derivative of mu times y. So if we integrate both sides, the final equation that we get is mu times y equals the integral of mu times q of x. Since we integrated this, we have an integral constant. So y finally would equal to this equation. So the answer to this equation is the integral of mu times q of x plus c, the integral constant, over mu, where mu was e to the p of x, the integral of p of x. So going back to the KCL equation, p of x would correspond to 1 over r times c, and q of x would equal to vs over r times c. And mu, since it is e to the integral of p of x, in our case it will be 1 over t over r times c. So if we substitute all these components into this original equation, the equation that we get comes in this form. Just to be clear, I wrote t, but this is in fact x's. But it doesn't really matter anyway, because we were writing y to be v of t, and x is supposed to be t, which is time. So if we try to simplify this equation, the equation looks like this. And if you look at this equation, we can see that these factors erase each other. So the final equation looks like this. And this kind of looks familiar to this equation now, right? So if we rewrite this in this form, it becomes this equation, where x is t. It's important to note that in our case, v to the infinity would equal to vs, because the voltage across this capacitor would fully be charged when time goes to infinity, and that maximum would be the voltage of the source. So let's find the value of c, and this is our last step. So if we rewrite the function as v of t, I'm just rewriting this, it would look like this. So if we plug t to 0 to this equation, the equation that we get would look like this. Now, since t is 0, this part right here would correspond to 1. So this is the final equation that we have. So C, in fact, would equal to the initial voltage. This is V of 0, so this is initial voltage, minus the source voltage. This was, in our case, V to the infinity. So the final equation, if we plug C back to this equation, the equation we get is this equation. And we can see that now this equation is the same equation that we used before.